Okay. Hello, beautiful humans. We're about to talk about secondary anisotropies. Everybody's favorite. Well, yay. Some of our favorites. So secondary anisotropies are all of the junk that gets in your way if you're trying to do what we just talked about. But it also contains very rich physical information about our universe at a great degree of redshifts, and I find them very exciting. So the goal for this lecture is to give an overview of what types of secondary anisotropies are in the CMB, and then give you a current status / updates on various measurements, again, to position you to understand CMB talks. So secondary anisotropies are any signal that is encoded after that surface of last scattering. This is an illustration from my children's book on neutrinos. That's why you see giant neutrinos flying around. They are not to scale. And this arrow is supposed to indicate some kind of scattering event or maybe a lensing effect, non-realistically, where a CMB photon, for the most part, travel unimpeded for a very long time before hitting our telescope. But some of them do become either scattered in the Anisotropies effect or lensed, and we have to take all of the signals into account. So in gravitational lensing, I'm sure you're all familiar with Einstein rings, right? And you can kind of make one in a CMB map if you put a simulated large lensing effect, a very large piece of mass there, into your Planck map, just as an example. But this happens across the sky. The photons are lensed because they have to traverse these gravitational potential wells as they travel from the CMB. What that means is there are small scale deflections in the temperature signals that you would naively see that are described by a deflection field. So this little cartoon shows that. You would see just some normal vector here to a CMB temperature and observe some temperature signal. And instead you get some n plus delta phi. What this means is you have a change in the translational invariance of your CMB map. So an unlensed CMB map is translationally invariant. You introduce lensing and it breaks the isotropy. And what that means is that you can reconstruct this lensing field by using a quadratic CMB combination. So a correlation between two CMB map instances. And you can also use something else in that estimator. It doesn't need to be lensing by lensing. It can also be galaxy positions or galaxy lensing, because galaxies too feel gravitational lensing. You probably are, if you're not a CMB expert, very familiar with galaxy lensing. You can use either the positions giving the location of these dark matter halos, or you can use their lensing effects as well and get to this lensing field. So we're interested in studying lensing because it probes the projected mass distribution out to high redshift, and the lensing power spectrum probes the projected matter power spectrum. And in this way, we can test lambda CDM cosmology. We're sensitive to general relativity. And again, we can constrain neutrino mass, as well as constrain this combination of parameters, sigma 8 and omega matter. And we have done this. So this is now this lensing power spectrum, kind of state of the field, where you have measurements from a variety of experiments. This was from some recent ACT results, so those are in red data points as well. And we are continuing to pursue this by mapping out more and more of the sky and using these cross correlations to constrain this power spectrum, or rather lensing spectrum. Bless you. And so what we have right now from ACT at least is a coverage of nearly a quarter of the sky in dark matter dominated peaks and voids, where here peaks are orange, voids are purple. And we've, again, I feel like a broken record giving these talks, very consistent with lambda CDM cosmology. And then you can do cross correlations with external data sets. I think one thing that is exciting to me about secondary anisotropies is their rich cross correlation with other parts of the electromagnetic spectrum. You can look at high frequencies and low frequencies and look at different astrophysical signatures and consider, for example, as shown here, dusty star-forming galaxy positions through Planck CIB measurements, and cross-correlate and show that, yes, dusty star-forming galaxies live where the matter lives, as probed by the dark matter distribution as revealed from CMB measurements. So here, peaks and voids are shown in white and black, and the overlay from the Planck CIB map is shown in these colorful topo map type overlay. Pivoting a little bit from lensing to a nod to polarization, lensing can turn your E mode polarization into B mode polarization. And this is a huge issue for getting to our tensor to scalar ratio measurements. So I think just as an exaggerated example to build intuition on how this is done, if you put a point mass in front of your E mode, suddenly it looks kind of curly and it can be registered as a B mode. So this is something critical that we are trying to measure. There's no real takeaway from this other than we need to account for this. And so I guess one thing is if you hear of delensing, that is using measurements of gravitational lensing to remove them from our map so we can measure the primordial signals that might be present in B modes. This is a signature that I basically can't pronounce anymore now that I live in Durham, North Carolina, because there's a city called Raleigh. It's very close to Rayleigh, and you cannot say Rayleigh, but Rayleigh scattering is an interesting effect that is predicted and has never been measured yet, and we're seeking to measure it in the near future, so it's something to keep an eye out for. We often will say that the CMB is a snapshot, which is a little bit of an oversimplification because it did not happen instantaneously. And during that epoch of recombination through some time slice, neutral species were forming and scattering CMB photons within that time that the CMB was emitted. And what this gives you is a frequency-dependent shift that results in a power spectrum effect, which can be measured. It's just incredibly small, and so we have not done that yet. These plots show you in terms of TT, EE, and TE what the shift would look like at two different observation frequencies. And this is a very small signal, as you can see, in terms of percentage. It's a fractional difference, and it's small. And I think that's about all I wanted to say about that. Now we're going to switch gears to my personal favorite effect, the Sinayev-Zildovich effect. So this is the case in which a CMB photon scatters off of an electron. And this can be anywhere in the universe, but it is most likely to happen in galaxy groups and clusters where the electrons clump down. This inverse Compton scattering changes the blackbody spectrum of the CMB and results in a shift that gives you a frequency-dependent signal. And so if you look at, what frequency is this? 100 gigahertz. Then you will see this decrement. And if you look above the null at 220 gigahertz, you will see an increment. I think a good way to look at this is just through the shift of the blackbody spectrum. So because you are picking up energy from this electron that is present in hot gas, you're taking your CMB blackbody spectrum and just shifting it over up in frequency. This is an exaggerated case, but it shows then you get a null here at 220 gigahertz. And below that, you will see a decrement from the expected CMB temperature. And above it, you would see an increment. We encapsulate this signature in terms of Compton Y. That's this Y parameter. It has no units. It is the number of scatterings times the energy gain per photon scattering. And you can express it in terms of this integral, which takes into account the Thomson scattering cross-section, and then is a line of sight integral of the temperature of that electron. So you need to make either some assumptions or have some knowledge of whatever temperature you're looking at in terms of the gas, and then the electron number density. This gives you a proportionality to the temperature shift you see associated with that effect. And you can leverage this in kind of two main ways. You can use the knowledge that you just have a CMB map. Here it is, it's in the sky. You can run some kind of matched filter on it and pick out high signal to noise clusters through the SC effect. So even just by eye, when you look at a map of the CMB, the most massive clusters will pop out because of this temperature distortion. The downside of this is that you are signal to noise limited, so you are mass limited. Less massive clusters will give you a smaller signal, and then you won't be able to go down beyond some floor depending on the sensitivity of your map. It's good motivation for us to make more sensitive maps. So on the flip side, you can use an external catalog from experiments such as optical surveys like the Sloan Digital Sky Survey shown here that are really good at telling you where particular kinds of galaxies live. And then you can use that information to locate clusters, or groups mostly, in the map. And they'll give you independent information about where you could be looking to use statistical methods to measure the effects and constrain physics. So right now we have and I think is it on the archive? It's about to be, I just reviewed the paper. We have a great deal of an expansion of our cluster catalog from ACT. Right now, as of this plot, we had from DR5 over 4,000 clusters cataloged. This too is a great jump in terms of, in just a few years, we've cataloged thousands of galaxy clusters through millimeter wave measurements alone. And this is just going to improve both in terms of mass and in redshift. So I had said that we're going to be mass limited, and that remains the case, but we will be pushing down in mass on the y-axis here and pushing up in redshift on the x. I mentioned that the Compton Y signature is not just relegated to groups and clusters, but is across the sky. You can trace the distributions of baryons across the sky by measuring the TSZ effect and give a measure of optical depth. And this, again, is not to be confused necessarily with the optical depth to reionization. Sometimes we were talking about individual objects. The TSZ effect is a unique probe of high redshift galaxy clusters because it is a largely redshift independent effect. And we can use it as a tool to understand the thermodynamics that are taking place inside of group and cluster halos. Right now, we have a situation where, I don't know how many of you have worked with the hydrodynamical simulation. I kind of ate that word, hydrodynamical simulation of galaxy groups or clusters, but you might have needed to decide on some subgrid physics assumptions. And those are really poorly constrained right now with empirical information. So by taking measurements of the SC effect, we can start to place constraints on feedback or non-thermal pressure inside of these systems and then feed that into our simulations to get more accurate simulations. And then combining the thermal SC effect with the kinetic SC effect, which I'll talk about, gives you a unique probe into both this astrophysics and also into cosmology, because it breaks an optical depth degeneracy associated with the information contained in these halos, and it gives you the ability to measure things like pairwise velocity, which I'll get into in a moment. This plot here is an example of what you can do when you use these optical cross correlations. So this is a sample of 23,000 luminous red galaxies, just averaged together. You can see the average decrement associated with those sources. Whereas if you look at any one of those, and it might just look like gobbledygook because it's just low signal to noise. Okay, well, we're switching gears to the kinetic SC effect. This is a temperature signal encoded in the CMB that is not due to the hot electron in the gas, but instead the bulk motion of the gas. So you see a Doppler shift of the CMB photons due to the motion, the peculiar velocity of the structure you're looking through. So if you're looking through the gas that is moving towards us here on Earth, a CMB photon will receive a kick in energy. And if you're looking through one that's moving away, it'll become redshifted. You can express this mathematically by relating the temperature distortion associated with the KSE effect to the line of sight integral, again, of the scattering cross-section and electron number density times the line of sight velocity in a simple form. And I will note that this too is relying on the optical depth of the galaxy cluster gas. And so if you want to measure the velocity, you need to have some independent information about that optical depth to measure velocity. And that's what we're interested in doing. The pairwise KSE estimator is just one statistical method of getting at this information in the KSE effect. There's a whole host of different ways to extract this very small signal, but I'll explain the pairwise one here. If you look at the temperature differences between 2 points, and you average them together and reconstruct their positions on the sky using redshift information, you can plot their pairwise, so relative to one another, momentum as a function of how far apart they are from one another on the sky. And what that will tell you is that structures that are relatively close to one another, like galaxies that are 40 megaparsecs from one another, will be experiencing infall due to the attractive force of gravity. And sources that are very far apart from one another don't really know about each other much at all, and so they don't have very much relative momentum. This is important because it's a probe of large-scale structure. Any probe of large-scale structure, generally, will be able to tell you something about the way that structure has evolved and give you some constraints on the parameters that dictate that, such as neutrino mass. So here you can see the simulation of what large-scale structure looks like with and without neutrino mass. You are all probably very familiar with this at this point. And the velocity plot then of this pairwise estimator shows the sensitivity, and it's quite small here because these are exaggerated cases. But if you had no neutrino mass, then your structures are going to be more overdense and underdense, right? The contrast is higher because you are putting less of your universal budget into neutrino mass, which runs away relativistically and smears out these structures. That means that in these overdense regions, you are experiencing more gravitational infall, and the peak of your velocity, your pairwise velocity curve, is going to be higher. If you put more mass into neutrinos, you are washing out the structure because they're free streaming relativistically at early times. That means there is less of an overdensity for those galaxy pairs to be infalling, and the peak of your velocity plot here is suppressed. So if we measure this very well, we will be able to constrain the neutrino mass sum in an independent way from the CMB and do all the neutrino mass sum things that we want to do. I'm not going to go through them. You already know and love them. We can also probe dark energy and gravity. And this is just, I like this pie. If you want to show a pie chart, might as well go literal. We are sensitive also to the dark energy equation of state parameter and the growth index because these two change the way the large scale structure form and therefore the infall of these structures. And so now I'm going to give you a little insight into the intuition here from some measurements we made of the pairwise KSE effect, where we divided our luminous red galaxy sample into 3 bins, low, medium, and high mass bins. And the way that galaxy cluster halos are distributed in the universe, we have fewer high mass halos than we have low mass halos. And that means our low mass sample gives us better statistics. With better statistics, we have smaller uncertainties, but also the signal is lower because these things are moving with less momentum because they're smaller. On the other hand, we have high mass samples. That means our signal is larger, but our uncertainties are also larger because we have fewer of them. Altogether, we can't make more high mass halos in the universe, and so what we seek to do is increase our sample size in general. So the name of the game with statistical measurements like the pairwise KSE approach is by maximizing the number of galaxies we work with. That's why it's very exciting that we're seeing these increased number counts of optical surveys that we can cross-correlate with larger CMB maps at higher sensitivity. This is just all going to boost our signal to noise and give us the ability to make measurements like this, which really require a great deal of sensitivity. A lot of work is ongoing to measure the TSE and KSE effects. In general, TSE is way easier. It has a much stronger signal than the KSE effect by about an order of magnitude. So we've been at high signal to noise TSE measurements for quite some time as a community. It's only as of late that we've gotten up to the 10 sigma level for KSE measurements, which is very exciting. Just a few years ago, this wasn't possible whatsoever. It's only through these improved measurements we can do this. And there's this result that I'm citing here that uses a different approach to measuring the KSE measurement, but again, over 10 sigma. And another interesting result from this paper is that it was shown at 40 sigma that the baryon gas that we trace through the SE effect is extended beyond the dark matter halo associated with that gas. This is a manifestation of this quote unquote missing baryons problem, which is no longer really a problem, but just a missing baryons fact that the baryons are outside of the halo where you would originally have expected them. And then up here, these plots are showing the stacked TSE signal, and I want to draw your eye to this dark spot in the middle. Does anybody know what that is? You know what that is. What is that? Yes, cosmic infrared background, or CIB emission. This is dust. This is dust that is having some kind of emission profile we'll show in a little bit and getting in the way of our signal. So you can try to remove it in various ways, and that is currently a big challenge for us that will become more important as we continue to be systematics dominated, or systematics limited, yes. So could this signal be radio emission? Yes, that's another thing we do need to account for. But I think if you consider radio emission, typically it's CIB that's contaminating across the sky in this particular way, but radio sources is something we do account for and try to remove to avoid that effect. Wow, look at that. I'm talking about emission and here we are. Okay, so there are a variety of types of emission that will get in the way of our CMB, like CIB, and kind of contaminate one another as well. So it's really important to try to separate out all of these signals. This is a set of plots from Planck showing thermal SC, kinematic SC, lensing, like we talked about, and CIB. And I'm going to run through some of these portions of foregrounds. I'm not going to go into any of them in extreme detail, but I'm just going to name and shame them because we need to understand them. So when you look at the frequency coverage of your CMB measurements, you're contending with a number of foreground effects, some of them more important than others, just because you can see them dominating at certain frequencies here. And in temperature, you see you get kind of a relief at the peak frequencies of your CMB measurements. In polarization, you are less lucky. You will need to contend with synchrotron radiation and thermal dust. So Bremsstrahlung, or free emission, is one of these kinds. We can point at it right here. Let's see, where is it here? In the blue. One of these kinds that is largely subdominant to the CMB in temperature and roughly associated with the galactic plane. One of the names of the game, one name of a game is to remove the galactic plane from your CMB. So when you're selecting fields, and I'll get into this tomorrow when we talk about survey design, is to simply avoid the galactic plane. This is where a lot of this emission is present. But this is produced from the collisions that occur between particles in hot and ionized plasmas. So here you can see an electron coming in, curving around this ion and emitting photons. And here you see an image of what free emission from our galaxy looks like. Dust emission is an issue in both temperature and polarization. Here you can see it dominates over the CMB for a large part of temperature as well. You can assign a spectrum to the emission associated with dust. And this is a large part of what we are actively trying to do. So there's some kind of modified blackbody spectrum you can write down. You also need to deal with polarized dust emission due to the partial alignment of these dust grains within the very beautiful magnetic fields in our galaxy, for example, is shown here. And this is another plot just showing the intensity of the thermal dust emission at frequencies, especially that are high. So another driver to go high in frequency coverage, to constrain your foregrounds, to remove them, to do CMB science. And this plot also shows you the TSC effect and how it dominates. It's dominated by dust at high frequencies. And here you can see one of the offenders. This is a protoplanetary disk, glowing bright. So CIB emission that you saw in the center of this plot right here is our issue that we're trying to deal with. We have thermal dust emission essentially from all extragalactic objects, but it's dominated by star-forming galaxies at redshifts between 1 and 2, roughly. We try to constrain it by measuring CIB at different areas of the sky. For example, there are these areas that Planck used for their CIB map creation. And then we can model this simplified modified blackbody spectrum here and try to remove it. So in this paper, if you're interested in reading more about it, there are a number of maps with different parameter choices in this blackbody spectrum model, and they all result in slightly different iterations of the map. And it does become important what your assumptions are if you are entering the regime in which you really need to account for this signal. So because of this, there are significant uncertainties that remain on the variations of CIB across the sky. And right now we're moving based on these templates. But if we could directly measure the CMB associated with these emissive sources or places on the sky, that would give us the best handle on dust removal instead of making some model that is then, it may not completely correlate with what is happening at a specific astrophysical source. So the best way to do it would be complete understanding of CMB emission all over the sky. And so that's another approach we're trying to work on by pushing to higher frequency measurements, for example. Okay, spinning dust. This is anomalous dust emission. It's a continuum emission in kind of lower frequency ranges. This orange line here. And it goes hand in hand with the other thermal dust, but it's just very excited, rapidly spinning dust, creating this kind of bump from extremely small dust grains. And this too is associated primarily with the galactic plane. And so you avoid the galactic plane, you are in fairly good shape, but it does become more important at low frequencies. And so to summarize thermal dust, both the spinning and non-spinning kind, you can estimate this as a modified blackbody spectrum. I liked this equation where your parameter choices are how much dust in terms of amplitude, how hot is the dust in terms of temperature, and what is the dust made of in terms of this beta parameter here. And it dominates everything above 100 gigahertz or so. Some of it is polarized, but the spinning dust has the lower frequency impact. Then there's synchrotron radiation, which go over here. That's that green line here, which becomes really important at lower frequencies and polarization. This is due to charged particles moving in magnetic fields and experiencing an acceleration. We don't have to read through all of this, but if you're interested in the details of synchrotron radiation, you can read this. There's a lot of this, actually. I'm not going to read all of this. We're going to get to question and answers instead. Here's what it looks like if you look at intensity and polarization. And I think the main takeaway here is that it does become dominant at low frequencies, needs to be accounted for and removed. And it's also more diffuse than just relegated to the galactic plane. And this is part of what makes field choice important when you are trying to make deep measurements. It's both dust and synchrotron and polarization. You're trying to find good patches of sky as well as to constrain and remove it. And finally, I have a slide on point sources. So this is that great radio AGN question for emission. Astrophysical sources are very bright and emissive, and you can see them just by eye in these maps. These are 3 different frequencies of the same patch of sky. You can see how the sources look a bit different in each place, but you can catalog them, write down what type of source they are, then remove them from your CMB map. That is what we do. And a paper just came out from ACT describing exactly where these sources are. So this plot is showing you on the sky where the catalog of emissive sources are and what type they are primarily emitting in. So if they're synchrotron-like or dust emission-like. And they are here. So we make catalogs, publish the catalogs, remove the catalogs. And these tend to be dusty star-forming galaxies, active AGN, and other pesky emitting dusty and gassy sources. And with that, we have arrived to the end of today. So we have talked about primary and secondary CMB anisotropies. You are now fully equipped to understand what people might be trying to measure. There are open areas of interest we went through. We talked about some complications, some foregrounds. And next time, I'm going to talk to you all about the instruments and survey strategies that we employ to try to improve our measurements to get after all of this. Thanks so much. Questions?
Thank you for the talk. It was very good. I had a question about the TSZ and KSZ. From my understanding, you're using, or there's a way of using it to understand large-scale structure. In the case of future CMB experiments, such as CMBS4 or CMBHD, the resolution that we'll be able to achieve is going to be far greater. will that help us in the signal to noise ratio, or will that make it more difficult to eliminate all these noisy parts such as dust and all these other things that you talked about?
Yeah, great question. And you're doing some excellent foreshadowing for some parts of tomorrow's lecture. So there is indeed the case that an improved resolution would help you resolve these objects. CMB stage 4 right now is not baselining larger telescopes than the 6-meter mirrors that are currently being used by ACT and soon Simons Observatory. So we're not expected to see much of a gain in resolution in our maps, but we will see remarkably enhanced sensitivity. This will give us improved signal-to-noise measurements of both the TSE and KSE effect, and will also help us remove these foregrounds, et cetera. So we're going to see an improvement in all of the types of constraints we can make with this. In addition, we're going to have the extended coverage of these new optical surveys coming out. So our statistics are going to be better for statistical methods as well. So in summary, everything I showed is going to be improved in pretty much every way, which is not maybe the most satisfying. If you have a specific science case, I could speak more to that.
How about in the case of like you have higher sensitivity from CMB-HD, which is planned way further down the line, so higher resolution. I know that believe they have bigger mirrors in that one.
Oh yeah, I mean, CMB HD, if funded, would be really fantastic. Yeah, that would be great to have the increased resolution in addition to the sensitivity. We will see some improved resolution, for example, from CCAT, just because we are going to be pushing to higher frequencies. And the frequency coverage at different submillimeter wavelengths will result in a naturally different resolution capability because of the instrument specifications that I'll have slides on for tomorrow. But we're, yeah, not banking on CMB HD yet, certainly not in the next couple of years.
Okay, thank you.
Yeah.
I had a question about the mitigation strategies you described, both in the context of the 2S effects and the point source removal. You could compare to a catalog and kind of mitigate that way, but wouldn't that also kind of incur the risk of having some kind of statistical selection effect or like seeing the wrong kind of galaxy? How do you correct for that?
Yeah, so I think what you might be indicating is, for example, the issue we were trying to address where we're assuming luminous red galaxies are proxies for the center of group and cluster halos. How do we know that that's actually the center? One thing you can do is wiggle that center a little bit. You can visually see in the thermal SZ stacks whether or not you are off or not, because the signal becomes very obvious with the higher mass samples. And it turns out that at least with our current sensitivity level, maybe in the future, if we have extremely high sensitivity data, this will become an issue. But right now, it is not a concern. The miscentering effects really are not limiting us, and you can test for them both simply visually and also statistically, moving that center around and doing kind of a null test to make sure you are centering and aren't miscentering to a degree that would exceed your statistical uncertainties.
Hi, great talk. I'm curious, so you mentioned that the main contribution for the CIB are from galaxies at redshift 1 to 2. So are there plans to use like DESI data from the tracers that are mostly emission line galaxies? Are you planning to use information from the recent DESI data releases for that?
That's a great question. I think that would give you positional data. I'm not sure how well that would constrain it in our frequency bands of interest, since we have to characterize the emission in addition to the locations. One thing you could do is if you had extended frequency coverage in the DESI sky area overlap, you could then use that as a source finding location to map out the emission over the sky. But as far as the galaxy information and redshift information from DESI, because it's not in our frequency bands that we need to constrain for, then it has its limitations there.
Thank you.
Freedom? All right, thank you all so much. This was lovely.